Okay, question 3. I think this is the first question in the tutorial that generated a lot of puzzled looks. So let's talk about this one in some depth. This will just be an introduction video to the problem, just talking about how you approach it and what you need to know in order to be able to solve it. And then the next video would be is going to be the actual solution to it. Okay, so we've got this device with wires hanging at with spheres hanging at the end of wires. We've got the mass of the spheres, and we know that both of them have got equal charges, which means when they were still down here, so they would have started down here, and then they would have felt repelling forces like this. And because they are confined to the ends of these wires, they can only move in circles, of course, right? Can only move in circles, like in a circle like this. I don't know if that's dark enough. Okay, so they can only move in a circle like this because they're at the end of the wires. Now, in the beginning, the repelling force is precisely in the direction of the circle in which they can move. So they have this very big force in the direction which they can move, and so initially they move away from one another quite with good acceleration under Newton's second law. But the higher up they go, the lesser the electric repelling force, which remains horizontal, because what happens here as well. The higher up they go, the lesser the electric force its component along the circle becomes, so the less inclined these spheres feel to move further up along the circle. Okay, so they only reach a certain height, depending on the charge. If you increase this charge, then the repelling force will be greater and it will move up a little bit more. But anyway, as it is, with the charge that it got and the masses that these spheres have, they came to rest in this position. And now we've got to find Q. Now this is a good example of a problem that there's a good chance you don't immediately know how to really approach it or how to solve it, which is very good, because just to contrast this with what I perceive to be the norm for typical high school tests and exams, in which if you prepare very well, then you can almost instantly recognize problems. Oh, it's this kind of problem which you solve in this particular way, with some slight variations perhaps. But a question like this, you might go, I need to find Q. I don't know how to do it. So if you don't know, don't freak out. And then you just got to blank sheet of paper on the test, which there will always be, and then you make a quick diagram and you see what the forces are and investigate a little bit. And if you know your stuff, then you'll see a strategy to solve it. So let's do exactly that. Let's go to a blank sheet of paper and see what's going on. Okay, so I've got my two wires with the two spheres hanging at the ends. I've got the masses, it's 21 grams. I've got my perfectly vertical line here. I've got the angle 26 degrees here, which is the same here, of course. And I've got the distances, 78 centimeters, okay. And I think what is happening with this sphere is just going to be just a reflection of what's happening here. So I don't think I have to analyze both of them simultaneously. So I'm just going to continue looking just at this one. Okay. So we know quite a bit about analyzing forces, and so perhaps we should do that. Let's see what are the forces acting in on one of these spheres. Okay. So on this sphere, what kind of forces are working in? Well, there's its weight, of course. The wire would also have a weight, but the question says we can just assume that it's massless, doesn't have mass, or we ignore its mass. Do we have this force? Yeah, we do. We've got the mass, so we can use just 9.80 meters per second squared for G. Okay, so we've got the weight. What else? Directly or horizontal, and away from this charge, there's going to be the repelling electric force F, and then there's also going to be the tension in the wire. Let's call that T. Now, because these little spheres are just hanging in the air here, and this position, that means net force on this little sphere, well, on both of them, but I'm just looking at this one now. The net force on this one is 0 because it's not moving anywhere. Oh, it's fixed in position. So in particular, it's not accelerating anywhere. Okay, so the sum of these forces are 0, in other words. Okay, so, all right, so we're making progress. We write down what we know, which is a great way to search for a way to solve a problem. If we don't know how to solve it, just write down what we know and ask questions. Okay, so I've got my 3 forces here. I know some of them must be 0 because of the static situation in which this instrument is. All right, now, what do I know about these forces? Tension, I don't know much about that, so let's ignore that for the time being. How about this? Oh, well, I already talked. I know this one perfectly. I've got that. Right downwards, of course, direction, everything. And I don't know about this one. I know it's directly away, so it is nice and horizontal, perpendicular to this one. Okay, and it's away. And what is its magnitude? Well, that is just Coulomb's law. Okay, times the absolute value of the charge on the one. Remember that one got a charge Q over 2. This one also has charge Q over 2. So absolute value of the one charge times the absolute value of the other charge over distance between them squared. Okay. Can I calculate this? What do I know and what do I not know here? Okay, I've used that a lot of times in problems, so that's just now proportionality constant from Coulomb's law, or the distance between them. Easy to calculate using trigonometry. It was this distance. How do you calculate that? That's simple. I mean, you just use 78 times sine of 26 to get this distance, and then multiply it by 2 for the entire distance. So R's no problem, K's no problem. So, interesting. So here I've got my first hint. If I can find this force F, its magnitude, then the charge Q is the only unknown, and then I've got Q. I just need to find F. So that's good. That gives me a direction to work in. I need to find F. And how do I find F? Well, I have to use something that I know about F, and this is the big thing I know about F, that sum of these forces equal to 0. Let's just simplify this a little bit quickly. This is going to be a Q squared over 4 over R squared. So this is just KQ squared over 4R squared. And this is also just Q squared. Right. Okay, so now to proceed further, you have to understand force components very well. And so to conclude this video, I'm just going to quickly go over everything I think you need to understand about forces and their components, and how to use that to add forces to get new forces. So let's quickly revise that. Let's say, where's my pen? Okay, here it is. Okay. Let's suppose I've got a force F here. There it is. Now, let's pick a direction. Which direction shall we pick? We pick any direction we want. How do we pick a direction? That will depend on which one is convenient, which one is interesting, or which one we feel like picking. So let's just pick this as direction. And then the other direction has to necessarily be perpendicular to it. So then that's our direction. Don't always have to think of these directions as having names. Normally it's X and Y, but let's use something else. Let's say this is the positive P direction, this is the positive Q direction. So arrow indicates the positive direction. So that's the positive P direction, that's the positive Q direction. Okay, so now this force can be said to have a P component and a Q component. What is the P component of this force? It is go from the direction line at the right angle upwards. So it must be somewhere like here, must be a nice right angle. So there you have the P component of F. So that is F, P. Alright, so this is the P component of F, or F's component in this direction. Right, and what is Q? Again, 90-degree angle, something like that. So there you have F's Q component. Okay, and let's say we know this angle. Let's say this angle is alpha. Suppose this angle is theta. We will only know one typically. Well, if we know one, we can calculate the other one. But we'll just pick one to work with normally. Right. Now, what is the purpose of this whole decomposition of f into two components? Well, it is the following. It is that f is now equal to the sum of its p component and its q component. And I said the two directions have to be perpendicular. Why? Because otherwise this isn't true. That you can decompose it this way in general is because you're picking two perpendicular directions. So why is this decomposition useful? Well, in the next video where we actually solve the problem, you see how thinking of the forces in terms of its component in two perpendicular directions, you'll see in the solution why that is intimately useful to solve a lot of problems. Right, so F is equal to the sum of its two component forces. Now what is Fp then, without the vector arrow? So what is just Fp? So what is F's p component? I'm sure we can call it this just F's p component. Not its component force, just what is Fp. Right, so is it positive or negative? Fp is the component force is in the positive p direction, so this is plus. And what is this distance? It is F, this distance times cos of this distance, like that. Similarly, what is F of Q? What is Fq? F's Q component is what? Not F's. It depends on the context whether I'm referring to the force or just the component in terms of the scalar. Whether I'm talking about the scalar or the vector, that depends on the context. So in this case, I'm talking about the scalar. What is Fq? First of all, is it positive or negative? F's component in the q direction is it is in the positive q direction, clearly. So this is also positive, so it is plus. And what is this distance? It is F times sine of alpha. F sine of alpha. F sine of alpha is this distance, which is the same as this distance. Or if you suppose you want to work with theta, or you can say if p is equal to, if you have, okay, what distance I'm after this distance, so it's the same as that distance, so it's F sine theta. F sine theta, also positive. And if q is what? It is, if I use theta, it is what I'm after this distance, and then it's F plus F cos of theta. Okay, now I won't always write the plus signs in front. This is just now to explain the concept in the revision of it. So normally I just write F cos theta, F sin theta without the plus signs. Okay, now how about if one of the force components is negative? So let's just do an example of that as well. So let's say I've got another case, I've got another force, let's say it is G, let's pick two direction, let's say that is my positive y direction, and let's say, and this is my positive, well, see, that's not nice 90 degrees, so let's be careful about that. Let's just rotate it, make it easier. Okay, let's okay, let's say this is close enough. That's supposed to be 90 degrees, all of it, all four angles. Okay, now let's just make this line a bit longer. Good. So what is the x component? What is g's component in the x direction? Okay, it is here. Nice right angle here. So let me just write it. Okay, so this is g's component force in the x direction, and what about the y direction? Here it is. There is the y direction. G's component in the y direction. Okay, and now notice when I'm looking at what these component forces are, it's this angle, the angle with the direction line that has to be perpendicular. This has to be perpendicular. Not perpendicular, this has to be a right angle. 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 The angle it makes with the direction line, not the angle it makes with a vector. If you're working too quickly, that is an easy mistake to make, and thinking that that this isn't the component force and thinking instead that it is here, it must make an angle like this and say that this is the component force in this direction, which would be wrong. So you won't probably easily make a mistake like this with a question like this, with a situation like this, but here it is. If you work too quickly, it's easy to make that mistake and say that it must be 90-degree angle with the component force, and say that the component force is not to here but a little bit further to here. So something like this, it's easier to make that mistake. So the 90-degree angle to get the component force must be relative to the direction line. Right. Okay, now same thing. G is equal to the sum of its two component forces. So what is Gx? In this case, is it positive or negative? Now in this case, Gx is in the negative x direction, so the component force in the x direction is in the negative x direction, so Gx is negative. And what is this distance from there to there? It is G. Oh, I need angles, don't I? So let's say this angle is, let's say it's alpha again. So that is alpha. So then this is minus G cos alpha. And Gy, is it positive or negative? The component force in the y direction is in the positive y direction, so it's positive. So it's positive G. What is this distance? Same as this distance, and this distance is G sine of alpha. G sine of alpha. Good. Okay. So then I'm sure you'll be able to deal with forces in that lie here and lie here. If the force lies here, the x component would be negative and the y component would be negative. If it lies here, then the x component would be positive and the y component would be negative. Okay, but let's look at a situation where we're trying to add two vectors. So let's say we've got two vectors. Let's say I've got a vector f here, and let's say I've got a vector G there, and let's say I've got my direction. Let's say I've got the direction here which I call S, and the other direction here is T, and let's say I'm interested in the vector V equal to G plus F. Okay. Right, so let's say I've got some angles. Let's say the two angles is, let's say this angle is theta, and let's say this angle is gamma. Right, let's add in the component forces. What is F's two component forces in these two directions, S and T direction? Okay, so right angle here, so there is F's T component force, and where is its S component force? Again, nice right angle, there it is. There's its S component force. Okay, now how about G? Let's do the same. Let's use different color. Let's use red. Okay, so there is going to be nice right angle there. You don't have to put these right angle marks here, just to indicate it for you. Okay, so that is G's S component force, and there is going to be right angle here. That is going to be G's T component. Okay, now let's see what is V in terms of these component forces. So V is equal to G plus F. So now I say, let's ask, what is V's? If I know what V's T and S components are, then I know perfectly what V is. So what is V's T component? Well, V is equal to G plus F, so V's T component is G's T component plus F's T component. And let's put brackets here to make it clear what they are. Alright, so what is G's T component? Let's see, where is G's T component? Here it is. There's its component 4. So what is this GT? Is it positive or negative? Well, it is in a negative T direction, so it is minus. What's this distance? It is G cos of gamma. So it's G cos gamma. Okay, now about the F's component. What is Ft? F's component in T direction. And is it positive or negative? It's positive, and this distance is this distance times cos of alpha, so it's plus. It's positive plus F cos theta. So right, gamma theta, right? And normally, the brackets are here just to explain it. I mean, I wouldn't ever write this like this in a memo or in a class problem. I would just straight away write this as g cos gamma plus f cos theta. So I would skip this step. Okay, so similarly, what is its s component? It's going to be gs plus fs, right? And okay, again brackets just to make it clear what's happening. And what is g's s component? Okay, is it positive or negative? Yeah, it's positive. There it is, it's positive s direction, and it is magnitude of g. Okay, what's this distance? Magnitude of g times sine of gamma gives us this distance, which is the same as that distance, so it's plus g sine of gamma. Okay, and f's s component, similarly, that's just plus f sine theta in this case. Again, I won't write this. Normally, I just write it this way immediately, plus f sine theta. Okay, and there you have it. That's how you get it to the components of v. Now let's just say for argument's sake that, where's different color pen? Oh, okay, here. Let's just say for argument's sake, you've got some actual values for g and f, and you calculate all of this, and you find that vt is, well, just based on this sketch, would you expect vt to be positive or negative? Well, gt, this looks much further negative than this is positive, so the vt might be negative. So let's say argument says this is something like works out to be minus 5, and vs is something like, I don't know, 17, let's say, and then v is then square root of 5 squared plus 17 squared equal to 5 squared plus 17 squared to the power 0.5, yeah, 17 point, okay, fine, 17.7, that is not the point of the exercise. Okay, so 17.7. Now I want to say what is, let's say it's newtons, for example. So now I want to write v is equal to 17.7 newtons, but this, I can't write it like this because this is vector, this force, say, and this is just a scalar. I have to include the direction. So what is the direction? So I've got the t direction here, I've got the s direction there, and I've got v has got negative 5, so it is there, distance of 5 here, it's 2 minus 5 here, and this is its v t component, and this is its, let's say, its s component up to 17. So the actual v is here. That is the actual v. So now, how do I say what is the direction of this v? Well, if it is x and y, then the convention is to simply give the answer anti-clockwise from the positive x direction. So if this was x, this was y, then you would work out this angle, which might be something like 130 degrees, and just say at 130 degrees, let's say, and that would be enough. Okay, but we're not working with x and y in this case, so now you've got to pick. I've got to pick an angle to calculate. So you've got some options. You can calculate this angle and get, let's say, 30 degrees, and then you would say it is 30 degrees from the positive s-axis. Or you can calculate this angle, and you might get, let's say, 60 degrees, and then you could say the direction is v is 60 degrees clockwise from the negative t-axis. So from here to here, that's clockwise, and you have to say clockwise, because if you don't specify clockwise or anti-clockwise, then the convention is that you are implying that it is anti-clockwise. Anti-clockwise is the norm. If you just provide the angle, then it's understood to be anti-clockwise from either the positive x-axis or what other axis you say it is from. Okay. So let's calculate this angle then. Let's call it alpha. So what is alpha? Okay, so alpha is in a little triangle like this. What do we values? We know that this distance is 17 and that distance is 5. So I've got the opposite and the adjacent angles to sides to alpha. So that means I can work out tan. It is 5 over 17, so alpha is okay. So I'm running out of space. Doesn't matter. I just want to show how to calculate the angle. So this is tan inverse of 5 over 17. Okay. And this is equal to 16 point, yeah, okay, fine, 16.3 degree, 4, let's just say it's approximately 16 degrees. Okay, so that angle works out as 16 degrees. So then you could just say this is 17.7 newtons at 16 degrees to positive S axis. You can write it like that. Or in other words, if you worked out this angle, then that would have been, what that would have been? Well, we already worked out tan inverse 5 over 17. Yeah, that's fine. Then it would have worked out tan inverse of the other way around, 17 over 5. And then, yeah, this angle would have worked out as 74 degrees. So then you could also have said that V is 17.7 newtons, let's say, at 74 degrees clockwise from negative d-axis. I didn't have to specify clockwise, anti-clockwise here again, because anti-clockwise is the convention. So this is implied to be anti-clockwise because I didn't specify. Okay, so there's multiple ways to answer it. Even a third way of answering it is just saying, look, V is 17.7 Newton, that is its magnitude, and V direction is 16 degrees from positive S axis. Okay. And that is it.